I'll be talking through the solution to question 6 of the 2016 examination paper for the unit Numerical Methods for Partial Differential Equations. So question 6 presents you with the shallow water equations, which are a system of these two PDEs, or in this case h is the water depth, u is the horizontal velocity, and g is the acceleration due to gravity. So part A presents you with the definition of Jacobian of PDE in this form, where u is a vector differentiated with respect to t, plus f differentiated with respect to x. Okay, so part 1 of the question A asks you to define the vectors u and f, and hence determine the Jacobian. So u, the vector u, are all the terms which are differentiated with respect to t. So here we have h for the first equation and hu for the second. So therefore this is our u vector, and f contains the terms which are differentiated with respect to x. So we have hu, and we have hu squared plus a half gh squared, which gives us our f vector. Okay, if we have a look at this, the definition of the Jacobian is in the form of derivatives of f1 and f2 with respect to u1 and u2. Okay, so u is made up of two components, u1 and u2. So u1 is h, and u2 is hu, and similar for f. So f1 and f2, where f1 is hu and f2 is hu squared plus a half gh squared. Okay, so in order to assess the derivatives, we need to write f1 and f2 in the form using u1 and u2. So f1 is hu, which is the same as u2, so that's quite easy. For f2, okay, so to make hu squared, we square u2, then we divide by u1, and a half gh squared is simply half g times u1 squared. Okay, so we evaluate the partial derivatives. The first two are fairly trivial. Derivative of f2 with respect to u1. Okay, so there's our f2 with respect to u1. Okay, so usual partial differentiation technique. You just assume that any term which isn't u1 is a constant. Okay, so this gives us minus u2 squared times u1 to the power minus 2 plus g times u1. Well, u2 squared is h squared u squared divided by h squared just gives us minus u squared plus gh. Okay, and similar for the derivative of f2 with respect to u2, we've got 2 times u2 divided by u1, which comes out as 2u. So therefore, put all that together, and we have the Jacobian. So part 2 of question A, use your Jacobian from part 1 to determine the wave speeds of the fastest and slowest possible waves. Well, you need to recognise or need to remember that the eigenvalues of the Jacobian give the wave speeds. Okay, so this is Jacobian is 2 by 2, so it's a simple 2 by 2 determinant with minus lambda on the main diagonal elements, and this gives us this quadratic function in terms of lambda. Okay, so use the quadratic formula to solve for lambda, and eventually we get lambda equals u plus or minus root g times h. So the slowest wave speed is u minus root gh, and the fastest is u plus root gh. Okay, part B, we're going to use the shallow water equations to model a dam break. The domain is 2 meters in length, and we're going to use 6 nodes to discretize it, so our spatial length is 0.4, our spatial step is 0.4. The dam or the partition is located at 1 meter, and so 2 bodies of water are separated. The height of the upstream body is 1 meter, and the height of the downstream body is half a meter. The bodies are initially at rest, that means the velocity is 0 everywhere. Zero gradient boundary conditions are used, and at time t equals 0 seconds, the partition is removed. So we're going to use the Latz-Friedrich scheme to solve the shallow water equations, which you're presented with on the exam paper. And B part 1 says calculate the maximum allowable time step using this formula here. Okay, so delta x we've already established as 0.4, that's quite easy. So for each node in the domain, we have to calculate the absolute value of the fastest or slowest wave speed. Well, it makes it easy for the first time step because u is 0 everywhere. So we can just ignore this term. And so we're only looking at the root GH. And h is either going to be 1 or a half, and we're looking for the larger of the two, so it's going to be 1. So the first time step, is, the maximum time step is delta x divided by root g. That's what we have here, which works out as 0.1277. Okay, why do we have to calculate delta t at each time step? Well, the values of velocity u and height h aren't going to stay constant. They're going to be changing. So therefore the maximum velocity in your domain is also going to be changing. So you have to calculate delta t for each time step. Okay, and the final part is perform one step of the Latz-Friedrichs method for all 6 computational nodes. So first thing I've done is delta t over 2 delta x, which is this term here. That's going to be constant for whatever node we're dealing with, so we can calculate that. It's quite an easy calculation. Calculate the coordinates of the nodes. Well, this helps us for the initial conditions. So here we have the ghost node, which is outside of the domain, so that's minus delta x outside. So the first node is on the left-hand boundary, and then we just go up in 0.4, and we get to the right-hand boundary, which is 2, and then we have a ghost node the other side. Okay, so the partition is at 1, which is halfway between these two nodes. So the first 4 nodes are going to have a height of 1, and the last 4 nodes are going to have a height of a half. And the water is initially at rest, so all those velocities are going to be 0 everywhere. Next thing we have to do is we have to construct the conserved variable vector, which, if I just scroll all the way back up, is this vector here, h and hu. Okay, so that's fairly easy. That's top line of the conserved variable vector is just h. Now the second line would be h times u, but of course u is just zeros, so that's going to be 0. The flux vector, well, the top row is going to be hu, which is simply the second row of your u vector, and the bottom row is hu squared plus half gh squared. So because u is 0, this first term is 0, so we just got whatever half g times this number squared is. Okay, and that gives us the bottom row of the flux vector. Now we can save ourselves quite a lot of effort here. I'm just going to have a look at the Latz-Friedrich scheme. Okay, you can see it's a half times the node to the left plus the node to the right in this first term, and we use the node to the flux value of the node to the right minus the flux value of the node to the left. Okay, so for example, for the first computational node, okay, I'm going to use the nodes either side. Now, if the nodes either side have the same value, this isn't going to change. Okay, so the only nodes which are going to change are this node here, which is node 2, because if I just talk through the node numbering, that's going to be node -1, node 0, node 1, node 2. Okay, so that value of the node is going to change because the values either side are different. Likewise, node 3 is going to change because the values either side are different. We go to node 4, which is this node. Okay, the values either side are the same, so that value of that node is not going to change. Okay, so we only actually have to work out the values of 2 nodes. Okay, so if you do u2, so we calculate, so u2 is this node here. Okay, so it's half of the node to the left plus half node to the right, minus the 1.596, which we calculated earlier, and that's the flux to the node to the right minus the flux of the node to the left. Okay, and then a bit of number crunching, and you get this value here. Oops, this value of u2 over here, and do the same for u3. Okay, well, it's actually the same. Okay, so that's u2 there, u3, and actually got the same values either side, so it's actually the same, which is a feature of the Latz-Friedrich scheme. Okay, so after one time step, that's our solution. So you can see only those 2 nodes have actually changed. So that's the solution for the conserved variable vector u. So if we extract the heights, which is the first row from U, we get our values for h. Now the velocities are the second row of U divided by the first row. And the reason for that is because the second row of U is h times U. So to get U, we just divide it by h.